Okay, for the last talk of the day, we're pleased to have Alexander Tyukov from Southampton talking about 4-point correlators and n equals 4 superangles from ADS5 bubbling joint.
Thank you very much to the organizers for the opportunity to present my work at this wonderful meeting. Today, I'm going to present you the new supergravity method, which allows to compute 4-point correlators in the very interesting setup from some specific solutions in supergravity. So as a motivation, let me say a few words why we're interested in computation of these objects. First of all, as you know, correlators contain all the information about the interacting QFT in general, and there are many interesting physical systems which are strongly coupled both in nuclear physics and in condensed matter. They can be studied using the standard perturbative techniques, which rely on the weak coupling expansion. So one has to rely on some non-perturbative methods. ADS-CFT correspondence provides such a tool because it's a strong weak duality, so one can use weakly coupled supergravity to compute strongly coupled effects on the CFT side. And that's what I'm going to use. The 4-point correlators are particularly interesting because they're first type of correlators in any conformal field theory, which are not fully fixed by the conformal symmetry of the theory, so they're dynamical objects. And at the same time, they also depend on the coupling constant of the theory, so they're not protected by non-renormalization theorems, which come from the supersymmetry. And if we succeed in computation of these correlators, we can use them to extract the strongly coupled CFT data, such as anomalous dimensions, for example, by doing double OP expansion of these correlators and extracting anomalous dimensions of the exchanged operators. As you all know, the standard holographic method to compute correlators is to use written diagrams. However, in practice, this method relies on the knowledge of relevant 3-point and 4-point couplings of the fields in the bulk. And in spite of all of the developments in the holography, there are still many theories for which this information remains unknown. Such example includes 2B theory on ADS3 times S3 times T4, which is due to the famous D1, D5 CFT, which is particularly interesting for the black hole physics. And if you want to compute 4-point correlators in this theory, we have to develop some alternative techniques which are not using written diagrams. And indeed, this method was proposed in the context of this theory. And the first non-trivial results, both about heavy light and all light correlators, were obtained using this method. It was done by many people over a range of years. And the goal of my talk today is to take a step further and develop a similar technique, or extend this one to the case of high-dimensional holography, which is ADS3. Which is ADS5 CFT4 correspondence. So I'll be focusing on the most well-studied example of the holographic duality, which is string theory on ADS5 cross S5, which is due to n equals 4 super Mills in 4 dimensions. I'll be working in the supergravity regime, which means that my results will be valid at the leading order in 1 over n and 1 over lambda. And in particular, I'll be interested in the half VPS sector of this theory. So let me remind you the content, the operator content of the half VPS sector. As you know, n equals 4 super Mills has 6 scalars in the joint representation of the gauge group. Out of the 6, I'll be interested only in 2 scalars, phi1 and phi2, from which I will form holomorphic and anti-holomorphic combinations, which I'll call Z and Z bar. And the single trace primary operators in the sector are simply given by the traces of the powers of Z, trace Z to the n. So these operators have conformal dimension equals to the U1 R charge. And the second class of operators, which will appear in this talk, are called multi-traces CPOs, which are simply the powers of the single traces. And what's remarkable that these single trace CPOs are in one-to-one correspondence with the supergravity fluctuations, which were studied and classified a long time before the discovery of the holography 40 years ago by Kim Romans and van Jugenhuizen, who classified all the fluctuations of supergravity fields on top of ADS5 times S5. So the idea of the method, which I'm going to show you, is following. I will replace the computation of the 4-point function of operators in the vacuum by computing the correlator of light fields, which are dual to the non-backreacting supergravity field, on top of the non-trivial supergravity background, which will be dual to some heavy state in the theory. So this heavy state will be created in general by heavy multi-trace operators. The fluctuations will be dual to the light operator, which will be the descendant of the chiral primaries. And first, using the standard holographic technique, I will compute heavy light-light correlator, and then I will take the specific limit, which I'm calling the light limit, to obtain the correlator of all light operators. So let me show you this in more details. First of all, let me specify the supergravity background, which I'm going to use. I'm going to take the famous bubbling geometry in 10D, which was found by Lin, Lunin, and Molasina. This is half VPS solution of the 2B supergravity, which has SO4 cross SO4 symmetry, which is reflected by the presence of two undeformed three spheres in the metric. And the field content of this solution is just metric and the 5-form flux. So the coefficients in the metric can be related to two functions, one scalar function z and one vector potential v. So this solution is going to be smooth in the bulk, which imposes the certain regularity condition for the function z on the plane y equals 0. So the condition is such that it can take only values plus minus 1/2 on this plane, and that physically means that physically determines which one of the three spheres in the metric smoothly shrinks to 0. So this can be pictorially represented as coloring of two-dimensional plane into black and white colors. I'm going to consider the solution which has the same topology as the vacuum, which in this picture is simply the black disk. So the deformation of the vacuum, which is called Riplon, was considered by Skenderis and Taylor in 2007. And the boundary of the black curve is given by this equation in the polar coordinates. It depends on two parameters, alpha and n. Alpha controls the size of the perturbation, and n is the frequency. It will be related to the conformal dimension of the chiral primary operator. So in particular, I'll be focusing on n equals 2, and later I will show you the result for n equals 3 mode. And one can also consider the superposition of such Riplons, which will also lead to some non-trivial correlators, as I showed you later. So the second class of the perturbations that one can consider generated by this curve, which is called hypertrachoid. So that's the equation for the in complex coordinates. W is a complex number which sits on the unit circle. For n equals 1, this curve simply reduces to ellipse, and for n equals 2, it looks like a deformation of the triangle with the rounded corners. So now let me quickly switch gears and tell you about the states which are dual to these geometries and the role that precision holography plays in determining these dual states. The dual state, the heavy state gives rise to the vacuum expectation value of light operators, which are simply 3-point functions of 2 heavy and 1 light operator. Precision holography provides the dictionary between these waves and the coefficients of the asymptotic expansion of certain supergravity fields near the boundary. This precision holography dictionary was developed again by the same people, and we can use it to constrain the heavy state, at least perturbatively in powers of alpha. So at the first order in alpha, we have to have the single particle carrier primary. But at the second order, there are 2 options. We can either have the double trace, or we can have the single trace of the same dimension. A simply represents the mixing coefficient between these 2 states. So recently, the ellipse geometry was analyzed by Justo and Rosso, and they argued that for the ellipse, there is no mixing between at the second order between single trace and double trace operator. So A simply 0. And although the spirit of the paper was absolutely right, the technical details of the calculation were incorrect. And we decided to revisit this computation, and we showed precisely that indeed this is the case, and ellipse doesn't have a mixing. And in the subsequent paper, these authors made much more precise statement that the dual state for the ellipse geometry is simply the exponential operator of the single trace. And independently, we also analyzed the Riplon, and we showed that for the Riplon, A is for the minus one over n. So the Riplon is indeed the mixture of both double trace and the single trace. So the takeaway message from this precision holography is that the geometry, which is due to Hypertrechoid, is given by the exponential operator of the single trace primary. Yes.
So from here, it looks like alpha would be unbounded.
Alpha, well, we considering this perturbatively, so alpha in general is small. Yes. But for the ellipse, in principle, alpha can be large enough compared to 1.
In the bucket system, the alpha here got to be less than 1.
Well, it depends on how you normalize. So for ellipse, for ellipse, I think alpha can be can go up to 2, 3 alpha.
You had the expression r squared is 1 plus alpha cos.
Wait. You mean here?
Yeah.
Well, this one is a Riplon. It has different parameterization. So the alpha for the Riplon maybe not the same as the perturbative parameter for this curve. Okay, so the takeaway message is that if you want to use this geometry for computation of correlators, it's much easier to start with a hypertrechoid because it's dual to the exponent of just one single trace operator. Okay, so the central charge of this solution is proportional to the conformal dimension of this heavy operator is proportional to the central charge of the theory with the coefficient alpha square. And if alpha is small but independent of n, this state can be called perturbatively heavy. But if you scale alpha all the way to 1 over n, as you can see, the conformal dimension will be of order 1, and therefore this state, the heavy state, will become light. And therefore, one can use this fact to take a limit of heavy correlator have a light correlator and replace it with a correlator of all light operators. So now we can compute, we can perturbatively compute metric, and it is also very convenient for the computation to bring it to the de Lorentz gauge, because in this gauge we don't have any unphysical gauge degrees of freedom. So all the gauge degrees of freedom are set to 0. So we can simply match the supergravity fluctuations to the operators in the CFT. So let me briefly tell you about the light probe. The light probe that I'm going to consider is x-dilaton, because it has the simplest possible bulk equation, simply box phi equals 0. And I'm going to solve this equation of motion perturbatively in alpha with the following boundary conditions. First, I will impose the smoothness of the dilaton in the interior of the geometry. And then I will use the standard holographic prescription. So the first term here is non-normalizable mode, which specifies the source at the boundary at some point n on the cylinder. And the second term is the normalizable mode, which encodes the response. So coefficient bi of x encodes the 2-point function of the light probe in this background. So the dilaton is dual to the descendant, superconformal descendant of anticarrier primary, which I'm calling dk. And the boundary condition essentially fixes the zero-order solution, which is proportional to the bulk to boundary propagator. And having known phi 0, we can compute phi 1 and phi 2 by inverting this operator. So at the second order in alpha, this coefficient bi is proportional to the correlation function of two single traces which come from the geometry, and two light probes which come from the dilaton. And now the rule of the game is to express the result in terms of the standard function to make the connection with the known results. I'll skip this. I'll just show you the result. The result in the Lorentz space is given by this amplitude. One can see that it has the correct behavior because it has only simple poles at s equals 2 and u equals k plus 4. And it also has a correct flat limit when all Mandelstam variables go to infinity. But this was the correlator of two CPOs and two descendants. To relate it to correlator of 4 CPOs, one needs to solve the superconformal word identity. Luckily for us, the superconformal identity is known, and we can relate our amplitude to the known result. The only thing that needs to be fixed is the overall normalization of the amplitude that I showed you on the previous slide. And once this is done, the rest of the correlator matches identically. So we have, thank you. So we have the exact matching for the infinite family of correlators. And the same technique can be played for the replon with the frequency 3. So we did this, and we found the exact matching for this infinite family 33kk. And as I said, we can also consider superposition of the replon. In this case, the interesting correlator appears at the order alpha times beta. And this correlator contains operators of all different dimensions. The first time this correlator was computed quite recently using Witten diagrams, and we almost effortlessly generalized this result to the infinite family of correlators. So now let me very briefly tell you about the ongoing work on how to include double trace in this computation. So we simply need to go to the higher order of the perturbation theory. In this case, to capture one double trace and 3 single traces, we need to consider the cubic order in alpha. And this is ongoing work, so we still don't have the exact result, but we showed already that the result can be expressed in terms of the standard D function, which gives us a hope that we'll be able to match this result with the literature and further generalize it. So we would like to, in future, we would like to consider the correlator of this type 3 squared 3 k plus 3, which will be based on the hypertrachoid with dimension with a number n, and further on we can also try to obtain the correlators with 2 double traces, like n squared kk for small n. And even more interestingly, it will be to consider the generalization of the same technique to the holographic theories in other dimensions for which we know the bubbling geometries. Yeah. And I'll stop with that. Thank you very much for your attention.
Questions?
About your penultimate point, do people know LLM geometries on ADS7 cross S4?
Yes, actually, it was in the original Lingwin and Maldacena paper. They considered both LLM solutions in ADS4 cross S7 and ADS7 cross S4. So it would be very interesting to consider to apply to develop this technique and to apply to these theories.
Maybe you said this, but like how much 4 specific field theory knowledge did you need as input into this calculation? Was it mainly just
okay, so those solutions are 11-dimensional, which means that we have to work with M theory. So the problem with that is that it doesn't have a dilaton. So M theory only has metric and 4-form flux. So the bulk equation for the probe will be more difficult, and one has to do more on the supergravity side to extract the correlators.
Yeah, but it wouldn't be too much of a problem if I don't know anything about the 2-0 theory. It's a bulk calculation, you're saying?
Yes, it's a bulk calculation, so it should work in principle. It's just as I said, there is no simple probe field that one can take in the bulk